Okay, hi everyone. The microphone is on. Wonderful. Welcome to another stream for the what's it called? Talking Math in Public Animation Generation Collaboration. And let's get right into it. Where is my screen? We have as our topic today the following prompt: Polyhedron net. Create an animation showing a net of a polyhedron opening and closing. And I assume that polyhedron is specifically meant to be a 3D object, but we will do a 3D object anyway. Doing 2D or 4D would be very weird in any case. So a 3D polyhedron opening and closing, we want to do that. And yeah, I will use Cindy.js for that as always. And Cindy.js is a JavaScript library, so we will have to have a website. The link to the code will be in the description as soon as I push the changes to the GitHub repository, and then you can see how exactly it is set up. And in the website, in the code for the website, we have Cindy.js included, loaded. At the bottom we have the usual Cindy.js setup. And we also have my animation package. We only will have one thing that actually moves, I think, the polyhedron opening and closing. So it's probably a little bit of overkill, but okay. And I will also use the Cindy 3D plugin. So it's here in the use line for the plugins, and it's also here loaded at the beginning so that it is actually present. Cindy 3D is in general very, very nice because it has a fantastic camera. It renders very, very quickly. It is a bit annoying to work with because it needs a separate canvas. So we have two canvases here. The first is the normal Cindy.js canvas, which is on the bottom, so we can't use it anyway for interactive stuff, but we don't do much interactive stuff here. And I set its opacity to 0, so we don't see it, it just exists, because otherwise Cindy.js won't work. And we have this dedicated Cindy 3D canvas, and the rest is the boilerplate code. If you watched the last video, you might already know what this means. So let's see whether it actually works. I guess I have to start the web server at one point. Now it should work, and it's zoomed out. So I'm doing this polyhedron. So we have our canvas. Let's open the console because I will make mistakes and I will need error messages. Right, so this is the Cindy 3D canvas at the moment. And yeah, we want to make a polyhedron. So to get the polyhedron started, we will have to draw stuff on the screen first. So let's start there. Where is my note? Let's remove the screen completely. What I want to do is, in making a polyhedron net, I want to start with a tetrahedron that should be very, very simple. Then I want to go on to make a cube, and at the end, if we still have time, maybe try to make an icosahedron, because if the system itself works properly and nicely, adding more faces and more vertices shouldn't be that big of a problem. And to start, I want to have I think it lags pretty badly, but yeah, we can deal with that. So I want to make this net here of a tetrahedron, and I want to fold that into a tetrahedron. So let's say this is the first, second, third, fourth, sixth. These are our vertices, so let's just try to render them on screen at a first guess. So we will have a list of points, and I will have to remember to go back to my screen again. So maybe I can make it a little bit larger. Is that good to read? I hope this is good to read. So we want to create a list of points, and at the start let's say for the tetrahedron, let's make a little triangle. Also, I still have GitHub Copilot activated. Let's deactivate that because that's too annoying if you have to think. Right. So we want to have the first vertex at the top and then 120-degree turns. That should be 210 and 300, right? And let's just see whether that works. So we go into the rendering function. For Cindy 3D, you have to write begin 3D and end 3D. This gives you some sort of parentheses in which all the 3D rendering is done. And then let's say for all points draw 3D, and then we have our generic running variable in Cindy.js, which is the hash mark. And if we jump over, we should see they are askew. So let's see what's going on there. Okay, the angle's obviously wrong. So it is interactive. You can see it here. This is standard Cindy 3D capability. We can fix the camera to a specific point, and we will do that in a minute for testing purposes, because at the start, the starting camera is always looking down on the XY plane, which might make it hard to see what we're doing here. But if we fix the camera, we fix the camera and can't move it anymore. But yeah, here, it works, it just is wrong. So let's go back 90 degrees. So let's just not think about it. Let's Cindy.js think about what the actual... No, it is right. Why doesn't this give a... I'm very confused why this isn't an equilateral triangle. All right. Oh, obviously. One mistake I will make a lot today. This Eng2Vec is one of my tools, and all my tools are more or less 2D tools. So these are 2D points. So we have to add a 0 at the end to our vector, and then it should be in the... It's still wrong. Why is it wrong? Oh, 90 degrees, not 90 radians. This looks correct. Fantastic. So we have our points. Let's make it look a little bit nicer. So what I want to do is a background, something dark bluish, and I want to have point color, which I will just make white, and this is also the line color. So now we have our 3 dots, right? And now we want to have the edges between the vertices. Let's call it vertices. Vertices, just to P for all vertices. In most applications, you will encounter the edges. Let's call it edges. The edges and facets of these polyhedra will be given by index sets. So not actual geometric information, but just the indices. Use the first and the second vertex to build an edge, for example. And this is what we are doing here. So for the first part, it's just a triangle, right? So we have 1, 2, 2, 3. I try to be consistent with the rotations in case that will be important later. And then we say for all edges The render order doesn't really matter here in 3D, but let's render the edges before. And then the same as in Cindy 2D, if we pass on 2 inputs to the draw function, it will make the edges. Argument is not a list, so what am I doing here? For all edges. Oh yeah, right, so I have to use the vertices and not the indices themselves. I have to use the vertices. Right, so we have our first triangle that looks very nice. Let's say point size 3D 0.5 and line size 0.2. Then it looks a little bit nicer, especially if we go up to the icosahedron, then we can see a little bit more of the facets. Right, and now we draw our first facet, so we make the same thing. Facets, and in this case it's just a triangle, so 1, 2, 3. And then the command is also very similar to the 2D case, for all facets, fill poly, and now fill poly 3D, and we use the whole index as the index set, and it should give this here. So it's green by default, so let's give it a custom color. I think this is called surface color by default, surface color. Let's make this a red. And now you see the light by default is also shining from the top onto our object, which makes it look very white. It's very reflective, so it's very hard to see what we did. So let's move the camera a little bit for testing purposes, even though we lose the interactivity. And camera in Cindy 3D is look at 3D. It gets 3 values. The first is the actual position. So let's say 1, 1, 1. We want to be above the XY plane, and we want to look at it as if it was like a piece of paper, so probably a negative Y value. The second value is the actual look at, so we want to look at the origin. And the last, what you always need for 3D cameras is the up vector, which tells you how to rotate and orient the camera, and we will use set up because we work mostly in the XY plane. And if we do that, we are way too close. So let's zoom out like this. Right. We are very... Is that better? Probably not. That's just... let's say 0.5. I want the tip to be something like this. Now we can probably see what we are doing. Right, and because we want to fold stuff, we have to do more edges and more vertices. So let's go back to my note. So we have the first 3 vertices, and now we want to have 4, 5, and 6. And I think the easiest way to get to the points 4, 5, and 6 is not trying to calculate their positions correctly, but just to see that, let's say this here, just to see that the vector from 1 to 4, why is this so small? Oh, this is, why is this so small? Somehow it is multiplying instead of adding. Okay, let's just draw it. The idea is that the vector from 1 to 4 is the same as the vector from 2 to 3, and that makes it easier when we go to, let's say, icosahedron to do the same. We only have to calculate one triangle precisely, and then everything else is relative to that, so that should be easier. And if we want to adapt that, we probably want to do something like vertices as vertices, and we add something. So what we just had, we start at the first one, and the same vector from 2 to 3, so this is vertices 3 minus vertices 2. That should be the next point. Let's look at it. Yeah, we have the point here at the far side. So again, let's zoom out a little bit more. Better overview, right. Yeah, now we can do the other 2 points. So the next one is the same in the other direction. So 2 minus 3, and for the last one we want to start at 2 and we want to go in this direction. That should be right. So I hope you can see it on the stream. We have our 3 new points, so new edges. So we have, what do we have? We have 3, 4 and 4, 1, and a few more triples. We have 1, 5, 5, 2, 1, 5, 5, 2, and we have 2, 6, 6, 3, 2, 6, 6, 3. Now we have our edges and the last facets. So we have 1, 2, 3 is the center, 1, 3, 4, 1, 5, 2, and 2, 6, 3, and that looks like the net of a tetrahedron. And this is, of course, unfortunately, maybe what you have to do, right? If you do work with polyhedron and you want to depict them, you will have to type out the vertices at some point, and you will have to define the edges and facets at some point. That's inevitable. But right. Now we can think about how we fold this. And in the last days, I was thinking a lot about how I want to do that. For the tetrahedron, it doesn't really matter. We can just do the calculation. We just have individual facets which fold together. But if we have more complex nets, like for example with a cube, there will be things of some facets, some sides of the cube attached to other facets, and they will have to fold accordingly. And I will only do platonic solids here. If you do it much more general, you will have different facets rotating and bending by different amounts of angles, and it will be a whole mess. But what I want to do is, if we have, you can see the mouse right here. If you want to fold, let's say this edge here, which is the 1, 3 edge, I think. We want to have everything that is attached here, which in this case is just vertex number 4, to rotate around that edge. And if there are more things attached to it, more facets, we want everything to be rotated around the edge 1, 3. So we start by listing 1, 3, and then everything that should be rotated around that, which in this example will be very over-engineered, but hopefully we can scale it up to cubes and icosahedron much more easily then. So let's see if that works out how I imagine it. First of all, let's take a browser and tetrahedron. Let's find out the angle of a tetrahedron. That's certainly rounded. Dihedral angle, arcus cosine of 1/3, right. So we have the dihedral angle. Dihedral angle is arcus 1 divided by 3. And now we can rotate with that. So, how do I want to call it? I'm imagining it that so if you go back and if you imagine we have a larger net that we have to, I want this center facet to be like the base plate glued to the table and everything folds towards it. So we want to have the facets directly attached to that fold a little bit, and then the facets attached to those also fold a little bit, and more and more and more. So we have this tree structure, this outward ripple of dependencies. In the center we have something that doesn't move at all, then we have something that moves a little bit, and so on. And here in this case we just have one, let's say, level. So we have level A. And now let's write down what I tried to explain. So at the start, so this is our, let's go back to the numbered, sketch. Right, where is it? So we do have our 1, 3 edge. This is our rotation axis, and then we want to rotate the 4, and this is what I want to write down. So we have, let's make it consistent. Let's go counterclockwise. So it would be 3, 1, and then 4. And from this list, everything else should follow. And let's start with 1. Let's see how it works. And we put the actual rotation in the calculation function, because that's a better place to do calculations here in my package. So we want to do for all, what did I call it? Level A. For all elements in our first ring around the base plate, we want to do something. We want to potentially rotate many things. There might be many things attached to it, so maybe do a separate function. Rotate set. It's a set of vertices. We want to rotate many vertices around this axle. So rotate set. This is the set we want to rotate, our generic running variable, and the angle, well, it's the dihedral angle, but we want to animate it, right? So we don't want to do all at once. We want to do it over time. So ease in out cubic T1. This is now the functionality of my package. Ease in out cubic means we start and end slow, which gives some sort of physicality to it. And T1 is the progress of the first animation track. And this is now back to this boilerplate here at the top. So debug information, we can ignore that. And this track data tells us we have one motion which lasts for 1 second. So let's make it 4 seconds. So we want to fold it within 4 seconds, and then we have a 1 second pause at the end. And for more complex animations, we would have more of these movements, more of these steps, but here of course we just have one. We want to close our tetrahedron. And for this first 4 second track, the progress, which goes from 0 to 100%, is T1. So this should move as soon as we implemented this function here. This should move everything correctly. So let's say rotate set. We are rotating a set. And we use an angle. So what we want to do is we want to do for all elements in the set, we want to do something. So we want to assume that the first two elements of our set give the rotation axis and everything else should be rotated. We want to use rotate 3D. This is a function from my package, which uses in the backend, if you're interested, it uses quaternions to calculate rotations, and it gets, what is the order? It gets a vector, it gets an axis, and it gets the angle. In this order we have to do stuff. This rotate 3D function assumes that everything is centered at the origin, in particular the axis. And in our case, the axis is the edge of the polyhedron, which might be anywhere. So we have to normalize that. So our vector will be the vector from wherever we are. So we are at set running variable, wherever we are. And we want to start at, let's say, the first element of our set. And the axis is the second element of the set. Yes, we have to make the vector. So the axis is now the vector. So let's go back one more time. So in this case, with our limited small example, we started this here. We started here. This is the first element. This is the second element, and this is one of the others. Right? That should now work. Vector axis, and we rotate that, and right, we have to set it. All right. So first of all, we have to. So in our set here, we have the indices again. So we have to use the actual vertices. And then, of course, what we are doing here, this rotation is the new position of our vertex. So we want to say vertices, so the vertex at that position, it should be our rotated one, and we still have to do the shift. Right, so just looking at this last line, we take our vector and we rotate it around the axis by an angle, and we add that to our anchor point, our base point, and this is the new position of the vertex we have, right? So if we go through the logic, we do something for every element in our weird level set, which is just this triple here. So we start with 3, 1, 4. So here set is 3, 1, 4. And then this will give, so for all, so this is doing it for all sets, which now would also do it for the first two, but the first two are on the axis. So maybe, I don't know, you can restrict it. So what I'm trying to explain here is that now this point here, for example, will be rotated around the axis itself, it itself is lying on, which I guess for our purposes it doesn't really matter, but if you have very large complex animations you might want to optimize that out. I will just leave it in. So we start with 3. So this here is 3, so vertex 3 and 1, which is vertex 1, and set hash mark is just everything in order. Let's see whether that works. And we rotate by the angle over time. So let's see. Something is wrong. What is wrong? Cannot define. What is going on here? For all. Rotate set for all. Rotate set for all. That's a comment. That can't be it, but let's remove it anyway. Oh, for all set, yeah. Okay, I'm iterating. Yeah, very stupid. I'm iterating over all the elements of the set, but I'm pretending that I'm iterating over the indices of the set, right? So I do have to say for all 1 to lengths set, right? And now we can optimize that out and by just saying 3. So now it skips over the first 2 indices because those are our axes, and then it will iterate through all of them. That isn't it nice? Okay, what's going on? So first of all, it's rotating in the wrong direction, and it is oh yeah. My typical mistake. So first of all, it's rotating in the wrong direction, so let's be lazy and make a minus here. And what I'm doing is I'm still not used to the setup of my animation package. I rewrote a lot in the back end. What I'm doing here, what happens is I define the vertices once at the very start of the animation, and then calculation is called once 60 times per second ideally. So in every frame it does rotate by whatever the angle is, but we want to make it incremental, and the easy way to fix this is to take the definition of the vertices and pack it into the calculation itself. This technically now redefines the vertices in every frame, which is not so good if you want to do something interactive or something very complicated. This will lead to a lot of issues, performance issues, but for most things it doesn't really matter. Fantastic. It's a little bit too slow, so for testing purposes. And it is rotating. It is nicely rotating, but it is rotating by the wrong angle. Because so the dihedral angle is the internal angle of the polygon, but if we rotate it from the flat net upwards, we have to rotate it by 180 minus that. And maybe don't call it dihedral angle, then let's call it rotation angle. And that looks now very good. Right. What do we do now? The other edges. So the other edges, that means other sets. Let me quickly look. So we go 3, 1, then we go 1, 2, and 5 attached to that, and we go 2, 3, 6 attached to that. And now it should magically work because we did all the hard. Fantastic. Let's get rid of the fixed camera for a second. And that's a perfectly looking little tetrahedron. Right, so that's how it works for a simple net where you just have the base plate and one facet glued to it. Let's see how a cube works out. But that's basically it. So what we can optimize is the camera is pointing at the center of the base plate, but I don't want to change that because then I would have to make adjustments depending on what polyhedron I'm using. So I'm too lazy for that. And just to appreciate what's going on, let's make it longer. Let's make it open in closing. So what we can do is we use triangle signal. Triangle signal T1. Triangle signal will now move the output from 0 up to 1 and down to 0 again, which should now automatically open it up again. And then let's make it loop. So here at the top we just tell the system, the package, what kind of tracks we want to have. We want to have 1 7-second motion, but only afterwards, when everything is set up, this track is actually existing. So it goes into what I called late setup, and we say tracks 1 looping probably should be true. And then it loops. Fantastic. Isn't it pretty? Right. We could end here. We folded a polyhedron as the prompt suggests, but I definitely want to make the cube to have this multi-level folding. And as I said, I want to go up to icosahedra, regular icosahedron. So, yeah, we just need, quote unquote, we just need new vertices. So let's go to our sketch again. So let's draw a cube net. Maybe something very simple. Yeah. So this is a cube net, and we can order the vertices 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So let's make it a little bit larger. So these are our vertices, and now we can see the levels, hopefully. So we have our, let's say we have our base plate, right? Which will be the center. Then we have level 1. Everything that is attached to the base plate directly will get folded just like we did now. Oh, let's technically all of that is one level, and then as a second level on top of that we have this part here. So this facet has to rotate around this edge an additional time, right? So this will be a second level, and now we just hopefully we hack in the coordinates and everything works because we did all the thinking beforehand. Let's see how it goes. So first of all, we delete the edges and we delete the facets and we delete the levels and the rotation angle, right? So the dihedral angle of a cube is 90 degrees. Don't even have to look that up. So this will be the rotation angle. And then we have our vertices. So let's make it round So let's start with our unit square. Oh yeah, that's unit square. Don't forget the set coordinate. Let's start with our unit square. So we have 1, 1. Let's go around this way. So we have -1, -1, -1. Right. And if we go here, we should at least see our, let's go to our debug camera again. Where is it? So we have our first square. We will have to zoom out again a little bit more. So then the next, so we have a lot of pairs of vertices that are added. So we have 1, 2, 3, 4, 5. So that should be enough space for everything. And then we have 1, 2, 3, 4. So you start at the top. So just as a reminder, this is what we want to recreate, right? We want to go 5, 6, 7, 8, 9, 10. And now I will just very boringly type that out. So we go up. So we have 2, 1 and 2, -1. Don't forget the 0. And then we will go in the negative direction. So -2, 1. No. We want to. So this is why I shouldn't do it as a live stream, but too late for that. 0, 0, and right, we have to go 2 units up. We don't have to go to coordinate 2. We have to go to 2 units up, so it's actually 3. Then the bottom edge is at -3, 0, and we have -1, 1. And then we have 3 something 0 -1, 1 and 5. Maybe that should fit the sketch. Zoom out a little bit more. Come on. All right, that looks like the vertices we want to have. Now we have to type out the edges. Where are the edges? So we have 1, 2, 3, 4. This is the center. Then we have 1, 2, 3, 4 additional facets and 1 more which is attached to it. So these are the edges. So this is 1, 2, 2, 3, 3, 4, 4, 1. Then we have 1, 5, 6. 1, 5, 6, 2. Then we have 2, 7, 7, 8, 8, 3, and 3, 9, 9, 10, 10, 4, 4, 11. 11, 12, 12, 1, and the last one, which is the weird one. So, and that should give the edges of our cube. So we could do the folding now. But let's do the facets again. So we have 1, 2, 3, 4, 5, 6. That makes sense. With 4. So the first facet is 1, 2, 3, 4. We have 1, 5, 6, 2. We have 2, 7, 8, 3, and 3, 9, 10, 4, 4, 11, 12, 1, and 11, 13, 14. Right. And that looks at least not totally wrong. And let's see whether our folding algorithm works. So we have to have, first of all, the A levels. So if you go, yeah, let's leave that here. So if you go to our sketch again, as I indicated with blue and yellow, here at these parts is more or less exactly what we already had with the tetrahedron, but here we have to fold more vertices over the 1, 4 or 4, 1 edge, and then of course we have to add the second level, but let's see whether the first level is actually working. And right, I will just do the same as with the edges and vertices, just type it out. So around 1, 2, we want to fold 5, 6. Around, I don't know what I'm doing. So around 2, 3, we want to fold 7 and 8. Around 3, 4, we fold 9 and 10. And now around 4, 1, around the 4, 1 edge, we want to fold 11, 12, 13, and 14. And if we do that, it looks like a nice little package, a nice little box. That's fantastic. And we see the second level, the top part doesn't fold over because that would be the second level. But at least it's working so far. Right, so we have another level, level B. And this is now, we want to fold around the 11, 12 edge. And what do we want to fold? 13 and 14. And right, of course we have to tell the program to actually do it. So we have here for all level A, do this rotation. So let's copy paste that line and write level B. Yeah, we have to fold level A first, I think. And it works. Fantastic. Let's get rid of the debug camera again. No, let's up. The zoom here is not so nice. How close I'm. Let's where are the points? Where are the vertices? Where is everything? So 0. Let's zoom out that way. Right, so yeah, but that looks perfectly fine. Fantastic. Right, so if we want to do more complicated stuff, we might want to have a better structure. So what we did here is we just define the levels more or less independently, and then we just copy paste this and say for every level do that. And of course everything here, because it's a regular polyhedron, everything is rotated by the same amount, by the same angle. If you have much more complicated polyhedra, irregular ones in particular, you might want to be more deliberate with your data structure, with your dependencies, with your thinking in general, but I think here that's fine enough. And yeah, I think that's good enough to stop, but we're close to an hour. I will still take a few minutes trying to find and put in the coordinates of an icosahedron, just because I'm curious whether it works. And obviously it will be what we just did for the last 15 minutes, just typing out the index lists for the icosahedron. So no hard feelings if you want to leave now, because that won't be very interesting right now. But yeah, that's basically it. This is how I would animate this. And yeah, let's try to find the icosahedron as next. So let's keep this scale here. I don't know how many levels we will have. Let's remove everything. I will definitely have 2, so let's just make it empty. Edges. Oh, that will be annoying, but yeah, okay. What is an icosahedron? Regular. So first of all, the angle again. This is certainly not angle. That's not a precise value. Okay. Icosahedral, dihedral angle. All right. Arcus cosine of minus square root of 5 over 3. Okay. So arcus of minus square root of 5 over 3. Right. And now we want to have a net. So icosahedron net. So here, this is a nice helping with math. That's a nice looking net. So which one do we want? No, I don't want to download. So which one do we want to take? Do we want to have the boring one, or do we want to? I think I'll take the red one. Can I think I will put it on my second screen and trying to look at it. So, right, so we want to have our angle. So we have, am I still? Yes. So onto WEC, we start again with one triangle. So this is 90 degrees and plus 120 degrees, and that should give us our triangle. And then we say vertices is vertices and we add something. So let's see, where do I want to start? So now you can see it, but I hope that's okay. Let's make this one here. So that will be hard, but okay. Vertices 1, So this is exactly the same what we already had. So let's see. This is 4, 5, 6, 7. That should be. I start at 4 and I go to 3, 1. Then I start at 4 and I go 3, 2. And I start at 6 and I go 3, 1. Let's see whether this. Oh, something is. Something is acting up. I don't know what. Oh yeah, here this here is acting up because it's empty. So let's just remove those lines for now. And now we have. Right. Something is still complaining, but okay. Vertices is vertices, and we add. So this is 4, 5. Oh, so probably 5. 4, 5. So this is also 4. Right. So something like that. And then we want to have. Oh, this is super annoying. I don't want to do that. I think I'll stop. I'll do it. I'll probably do it off stream for later, and then you can find it in the description. But typing out those coordinates, this will be without. I will label the net I found on helpingwithmath.com and trying to do it, but no. Oh, that's annoying. Let's embrace the cube. Let's go back to the cube for a second. So yeah, official end at the cube. No, that's not fun. Yeah, I hope you enjoyed it. This is how I would animate this folding animation. And as I said, if you go to the repository in the link in an hour or so after the stream ends, you can find, as an example, the icosahedron. And here live on stream we have 2 other ones. So yeah, see you in May.